However, second volume type method. This is going to be using a shell method. Now, some students think the washer method's easier. Some students think the shell method's easier. I'm one of those that usually does the washer method. I'm not saying it's always easier. I don't know why. I just usually gravitate to that. Probably the closest thing you would remember would be in trig doing law of sines or law of cosines to solve a triangle. Sometimes both would work. Sometimes only one would work, but usually you would try the one that you liked better to start with. If it didn't work, you'd go to the other one. So we're going to work shell method today. When it comes down to it, what we're going to work over the next few days will be just finding volumes. So you have to decide which one you want to use. Okay. So you'll kind of see which one you like better after today. That's probably what you'll gravitate to start with first. And then if you can't get it to work, you'll switch to the other. Okay. Where we run into a problem with something that can't work both ways, you'll need to write this down. So let's say I had a function y equals 3x squared plus 2x. All right, now I can't solve that equation for x because of the two different powers. So when we did the washer method, we ran into a case when we switched which way it was rotating, we solved for the other variable. This would be a situation where you can't solve for the other variable. So if I was trying to do a washer method around a horizontal axis of revolution, so going this way, that would be x's. It's in x's, I'm good. If I wanted to go around a vertical axis of revolution, I'd have to have y's. I can't solve that for x, so now I can't do the washer method. Does that make sense? The shell method flips it. On the shell, if you have a horizontal axis of revolution, it has y's in there. If you have a vertical axis of revolution, it has x's. So something like this, wherever I was going, if I had a horizontal axis, I'm going to go washer method. But if I had a vertical axis going this way, I'd have to flip to shell to keep x's in there. That would be the difference. Right? And we'll see some different types mixed up over the next couple of days like that. Right? But that's the primary reason there's two different methods. Now, this part in front, this y or this x, I said is the distance from the axis of revolution. The part that I would suggest is if you're going around the, say, x-axis, I would do that front piece as y minus 0. You don't need the 0, but it'll remind you that's how far you were from it. Okay? Because if I was going to go around y equals 2, well, it'd be y minus 2 or 2 minus y. It wouldn't be a 0 anymore. The standard formula looks like this and doesn't show you a 0, but just realize we saw it last time, you're going to see it again, that axis is going to change. It's not always going to be 0. So I would encourage you to write this as a y minus 0, especially in the beginning here, and this one down here is x minus 0, just to remind you it's around that axis you're talking about, how far you are from it. And we'll get some different setups here. All right, so when we go through the problem, we're going to do kind of like we did before. We're going to focus on getting the setup. Your calculator will evaluate the integral. Not too much worried about that. All right. So let's go with this. Bounded by x-axis on 1 to 2 and f of x equals x squared. So first thing we want to do is just like what we did for area, just like what we did when we were talking about a washer method, we need to know what region we're talking about. Right? So either I need to, in my mind, have a sketch going of what it looks like or draw it out, whichever works best for you. I would imagine for most of us, having a quick sketch probably makes it a little bit easier. What we've got. So x squared, looks like this. X-axis down here. And on 1 to 2. So there's 1. There's 2. There's what I'm looking at. And I mentioned before, hey, that's fine. Maybe you're a person that likes to redraw or it's just that region, that's fine too. Whatever works for you. But I'm focused on this region right here from the point 1, 1 to the point 2, see 2 squared is 4. There's that piece I'm looking at. I think the more that you do, the more you get used to it, the less you need of a detailed sketch. Sometimes in the beginning it's nice to have all the points there and things like that for what you're looking at. So you get used to it. All right. So we're going to look at shell method. And we're going to go first about the y-axis. All right, so we're going to do kind of the same thing we did last time. We're going to take this region and move it around some different ones so we can see how the formula will switch around. Okay. So if we're going to go about the y-axis, so the y-axis is a vertical axis of revolution. Okay. So the toughest part for you to get used to here in the beginning is going to be the variable switched. Washer, horizontal, X. Shell, verticals, X. Flip. So about the y-axis, let's see, we're going to have volumes, 2 pi. I've got that vertical axis of revolution, so that's going to be my x's. So I'm going to have 1 to 2. Those are my x values in the region. Okay. How far am I from the axis of revolution? I am x minus 0 units. X minus 0 because the y-axis is x equals 0. Inside, top minus bottom, x squared minus 0 dx. Now, nothing's going to change as far as area, washer, now shell. It's always top minus bottom, right minus left. So if you're at x's inside here on the front, top minus bottom. If you're in y's, right minus left. Nothing's changing about that. So when I look at this, the curve, there's my x squared, is on top of 0 the whole time. Everybody okay with that? Now, again, I would encourage you in the beginning, put the zeros in. If you check an answer key or something, it's going to make the leap to right here. And a lot of times you'll wonder where the x cubed came from. We'll just multiply it out. But having those zeros in there is what's going to help you a little bit. Keeping track of. So here in the beginning, put them in there. Okay, let's go about x equals negative 1. Look at our figure there to the left. X equals negative 1 would be even further to the left, right? So we're still going a vertical axis. 2 pi. Still got x's because it's vertical, so still 1 to 2. Now this first piece is going to be x minus negative 1. Then I'm in x's, top minus bottom. X squared minus 0 dx. Now again, I know x minus negative 1 is x plus 1, okay? But I'm thinking it was x minus 0. So I'm saying that this one was x units from my rotation. Since I'm going around this guy over here, it's now x units plus 1 more. Because it's x units from 0 plus this extra one. Here's where that's coming from. Right? So again, I know you would write that as x plus 1 or think of that. If I went to my calculator, I'm going to put x plus 1 in. Matter of fact, I'd probably go ahead and distribute that because my calculator doesn't like parentheses very much. But write it like this to help you. Let's go about x equals 7. Now look at where that 7 is. That's over on the right side of your figure. That's over here. That's okay. It's still a vertical axis, which means there's still x's in there. So I'm still going to have volume, 2 pi, 1 to 2. I've still got x's. This distance from the axis of revolution is 7 minus x, not x minus 7. Why? Right minus left. It's always right minus left or top minus bottom, depending on what you're looking at. So 7's over here on the right, 7 minus my x units. The negative 1 is here on the left, x minus negative 1. So 7 minus x, and then we get the other part, top minus bottom, x squared minus 0 dx. Okay there? Okay. About x-axis. We're doing shell. So this would be a case where if I was taking a test, you asked me to go about the x-axis, I'm probably doing washer because I can see top minus bottom really good, keep my axis, but we're practicing the shell method here. So if I'm going to go around the x-axis, this means I'm going to have y's in there. If I have y's in there, that means it's going to be right minus left. Are you okay with that? So I'm thinking y. All right, I look at my shape. And I've got a little bit of a problem here. This vertical line is not on the right side of the function the entire time. It's only on the right side of the function from 1 to 4. It's on the right side of the other vertical line from 0 to 1. It's going to make 2 separate integrals. So again, I'll redraw my picture over here. We're looking at this guy, this piece. All right, here comes the other one. So here's that other vertical line. So I have one region right here where the green's on the right side of the black. And then I have another region on the bottom here where the green is on the right side of the purple. That green vertical line is not on the right side of the left side the entire time. It's 2 different left sides. Does that make sense? That's what's creating 2 integrals. Now, we didn't have that situation going the other way because we were top minus bottom, and this curve x squared was on top of 0 the entire time. From 1 to 2, stayed on top. But when I'm looking right minus left, it splits. And that split would be 1, 2, 1, and that was 4. So from 0 to 1 is the first split, and then from 1 to 4 is the second split. So I would start, I'm going to do the 0 to 1 one first. Doesn't matter which one's first, we got to get both of them up there. Just going to work from the bottom to the top. So 0 to 1. I am going around the x-axis, so how far am I from the x-axis? Y minus 0. Right minus left. 2 minus 1 dy. They're vertical lines. Again, I'm looking at the purple square there. Plus 2 pi integral 1 to 4. Now I'm going up to the green. It's not a triangle, but kind of looks like a triangle. Still y minus 0. Right minus left would be 2 minus root y dy. Remember, I have to have y's in there, and that original function was y equals x squared, so that means x equals root y. Solve for the other one. Okay there? Now you've gotten used to looking at different figures, either through the washer method or even from area, and looking at it and seeing what's on top, what's on the bottom, what's on the right, what's on the left. So that's why this shouldn't be too bad to see right here that we have a different function on the left from 1 to 4 than we had from 0 to 1. That's what's making two integrals. Now, if I change something here and I say 5, let's go about the x-axis. Let's go about y equals negative 3. It would be the same as number 4 with one exception in each part. What changes? 0. Instead of y minus 0, what would it be? Y minus negative 3, which turns to y plus 3, right? That's the only thing that changes. It's that front piece. So a lot of times on the shell method, people like it because there's not a lot changing. It's just that front part, that distance. So that y minus 0, if I went about that, y minus 0, I'll just write it up here, changes to y minus negative 3 in that front of each one, instead of rewriting the whole integral. So what about number 6 here? What if I said about y equals 8? What would the y minus 0 change to? Y8 minus y and not y minus 8. Top minus bottom. There we go. So y minus 0 changes to 8 minus y. Always keep track of that top minus bottom, right minus left. And I know for me, still to this day, I don't need this nice detail. I usually still have to see some kind of picture so I can remember which way it's going. You know? And half the time, if I'm sitting there working it out, or if I'm even working out a test, I'm sitting here doing this. Figuring out which way it's moving. Okay? So you got to keep track of which one you're working with. Okay? But okay there?